All right, so moving on to now to something called modular congruence. We've got this idea of mod that we just introduced, which is basically like taking the remainder after a division. And so now we're going to kind of spin off on that mod idea and produce this sort of like equivalence between numbers, which is called a congruence, and based on the idea of mod. And it goes like this: a number a is called congruent to a number b modulo some specified number m if that number m divides the difference between them, a minus b. And actually, whether it's a minus b or b minus a is irrelevant, because those are just going to be opposites of one another, and m will divide. If m divides one of them, it will divide the other one as well. So like, for example, if like 5 divides 10, but 5 also divides negative 10, so it doesn't really matter what order that subtraction is done in. By the way, and the notation, so once you've established A is congruent to B modulo M, the notation is like this. We use the triple equal sign again for congruence, and then we write in parentheses mod whatever that M number was. So an example of this would be like, an example would be something like 12 is congruent to 27 mod 5. Why is that? Well, since if you take 12 minus 27, you get negative 15. And 5 does divide negative 15, right? So the difference between 12 and 27 is negative 15. However, there's also an alternate definition that you could take for modular congruence, which might be a little bit easier to think about, because this idea of taking the difference between these numbers, like subtracting them, and then checking to see if it's a multiple of 5, if like does 5 divide that, that's a little bit, I don't know, it feels like jumping through hoops a little bit here. There's an alternate definition, which is perhaps more immediate. It's that A is congruent to B mod M if A mod down by M, like reduced modulo M. This is the mod with the underline that we introduced in the last video. This is the bold mod. This is like, the percent operator from programming. So A mod M if that equals B mod M. So essentially it's saying if you divide by M and get the same remainder. So in that alternate sense, the reason 12 is congruent to 27 mod 5 is because 12, if you reduce mod 5, gives you a remainder of 2, right? 12 is 10 plus 2, and that's, 5 times 2 plus 2. So it's a multiple of 5 plus 2, with the plus 2 in particular being your remainder that you take. And then 27 reduced mod 5 is, what's the remainder when you divide 27 by 5? Well, it's 25 plus 2, right? So that's also 2. 27 is 25 plus 2, and 25 is a multiple of 5. That's 5 times 5, and then plus that 2. So they have the same remainder when you divide by 5. So that's the definition of being congruent modulo something. What it does is it takes the entire set of integers, right? Let's take like negative ... negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10. Let's do a few more. And then if you look at like say you want to do like what is congruent to 3 mod 5. Okay, what's congruent to 3 mod 5? Well, what you can do is take like look for multiples of 5, starting with 0. 0 is the simplest multiple of 5, and then add 3, right? 3 is congruent to 3 mod 5. Find another multiple of 5, and then add 3. 1, 2, 3. 8 is congruent to 3 mod 5. Find another multiple of 5. Here's like 10, and then add 3. 1, 2, 3. 13 is congruent to 3 mod 5, and so on. What else is congruent to 3 mod 5? You'll notice it's also, not only is it 3 more than a multiple of 5, it's 2 less than a multiple of 5. So in fact, like -2 is also congruent to 3 mod 5. So all these numbers that I've got circled here, these are all congruent to 3 mod 5. And in fact, they're also all congruent to each other, because it turns out this is it's the type of thing where like it's transitive, which means that if A is congruent to B and B is congruent to C, then A is also congruent to C. So it like kind of like spans through. So since these two are congruent and these two are congruent, these two are also congruent. And so are, since these two are, well then so are these two and so are these two. So they're all congruent to each other. And they create what is called a congruence class. And the team that is going to be doing a project on chapter 9 will be doing, they'll be studying something called relations, which is kind of like it's kind of like a more general idea of a function without as many restrictions. So it's a very, very general mathematical idea. But one of the things you'll study in chapter 9 is something called an equivalence relation. And this modular congruence is an example of an equivalence relation, and they create things called equivalence classes, and that's what this congruence class is. It's the set of all integers that are congruent to each other modulo some specified number, like in this case, modulo 5. So I want to give one more example of this idea, not like a mathy example, more of a real world example of where this congruence comes up. And that's with military time, or what you could call military time or European time, military/European time. When you say, like in the military, they'd say like 1800 hours, right? Or 18 o'clock or whatever you want to call that. We interpret that as 6 o'clock, right? 6 p.m. And the reason we do that is because what we do is we actually take the number 18 and we reduce it modulo 12, right? 18 is congruent to 6 mod 12, okay? And in fact, like 18 reduced mod 12 is equal to 6, right? The remainder when you divide by 12 is 6. So, I mean, and if you're familiar with this, comfortable with this idea of converting time, saying, well, just subtract 12, right? That's like finding the remainder after division by 12, and that's an example of this idea.